Okay, this deals with the titration analysis of aqueous solutions of electrolytes. And a titration is a practical test protocol where an aqueous solution of known concentration is added into a specified volume of solution having an unknown concentration for the purpose of determining the reactive behavior and or stoichiometric nature of the reacting system of interest being studied. Now, I'd like to look at some aqueous electrolyte systems that are examined by titration analysis. We can examine salt metathesis reactions, acid-base metathesis reaction, and oxidizing agent and reducing agent redox reactions, oxidation reduction reactions. Okay, let's look at some examples of reactions that are analyzed by titration process. First, let's look at the salt-salt metathesis reaction. Here's an example of the salt-salt metathesis reaction that ends in a precipitant to NaCl aqueous when added to lead nitrate aqueous forms 2NaNO3 aqueous and PeCl2 as a precipitating solid. So if you were interested in determining the quantity of chloride or lead nitrate needed to initiate a precipitation, you could titrate sodium chloride into lead nitrate solution, and when the appearance of the solid occurs, then you would stop and calculate the appropriate concentrations. Now, working with the salt-salt metathesis reactions, this is a molecular reaction. From the molecular reaction, we can get an ionic equation, which looks like this. And shows how each compound, ionic compound, breaks down and delivers cations and ions in solution on the reactant side. And produces solution with that technically delivers 2 sodium ions. It'd be a spectator ion plus 2 NO3 negative ions aqueous plus lead chloride as a precipitating solid. And if we exclude sodium and the nitrate from both sides of the equation, we can write a net ionic equation. And this would show only those ions which actually undergo reaction, the lead and the chloride. traditionally the metal is shown first, or cation, plus chloride, forming the lead chloride precipitate, the ionic precipitate. The spectator ions of course are sodium ions in solution, and the nitrate ions in aqueous solution. The driving force of the reaction, and is typically shown as an equilibrium, is the precipitation of lead chloride. Or precipitation. Next, we look at acid-base metathesis reactions, and as I present these examples, I want to present 4 acid-base reactions in that you have a strong acid, strong base reaction, type reaction. Then you'll have a weak acid, strong base, weak base, strong acid, and weak acid, weak base. We'll start with, of course, the strong acid, strong base. And in this case, we'll use a common hydrochloric acid reacting with sodium hydroxide, aqueous, producing the salts, sodium chloride, aqueous, plus the driving force in this case will be water. Typically, a strong acid-base metathesis reaction produces a salt plus a weak electrolyte. Well, the ones I'm showing you will all come out with water, but there are acid-base reactions which do not produce water, so they produce a weak electrolyte. That's the driving force. Next, we look at a weak acid example. And a strong base, where the weak acid in one solution added into a base solution. Let's use acetic acid, HC2H3O2 aqueous, plus the strong base, sodium hydroxide, aqueous, produces a sodium acetate salt, plus water as the driving force of weak electrolyte. We can have a strong acid and weak base titration, in which we could hypothetically say HCl, aqueous. There's also HBr, HI. HNO3 is a monoprotic other strong acids. HCl plus, say, ammonium hydroxide. Aqueous goes to the ammonium chloride salt. Again, the weak electrolyte, and this reaction is water. And finally, we can use a weak acid and a weak base. If you so wish, and here acetic acid, say, as an example, might be used to titrate a weak base. That goes to ammonium acetate. Plus H2O as a liquid in this case. So we have 1, 2, 3, 4 acid-base reactions. Now the implications of using these leads to many other topics relative to the products that are produced at equivalence points. So, but at this point I just want to identify the possibilities in the acid-base reactions and metathesis reactions that can be applied to titration analysis. Now, oxidation reduction reactions are also adaptable to titration analysis. Here's one in which potassium permanganate solution, a KMNO4 aqueous solution, is added into an iron 2 aqueous solution and evaluated by a titration analysis. Now, in order to do a reaction like this, we'd have to have the balanced oxidation reduction reaction. And the ionic equation of this interaction is, say, we can put the iron plus 2 aqueous plus the MnO4 aqueous minus, where the MnO4 is your oxidizing agent, and iron is your reducing agent. Like that. And when these react in an acidic medium, we produce iron 3, which undergoes reduction, and aqueous, and manganese plus 2. And if it's in an aqueous medium, this will balance out with 8 moles of hydronium ion, if you wish. And on the reaction we have 5 moles of iron, 5 moles of iron 3, and finally 4 moles of H2O liquid. So this would be set up primarily to identify the concentration of iron extracted from, say, an iron ore sample in an acid, and then you titrate it with the MnO4. Now, what you need to understand is that MnO4 minus aqueous ion is purple in solution, and the titration of, say, potassium permanganate into the Fe+2 aqueous solution remains clear, uncolored, clear, has no color, remains clear until all of the iron 2 aqueous has been converted via reduction, via oxidation, excuse me. Reducing agent, it undergoes reduction, converting via oxidation to the iron 3, the ferrite ion, ferrous to the ferrite. Okay, like that. The solution will remain clear, like I said, until we've converted all of the iron 2 to iron 3. Addition of more MnO4 minus aqueous ion causes solution to acquire a purple color, indicating that equivalence point conditions have been achieved. From a stoichiometric standpoint, iron 2 is being converted at a rate of 5 times faster than the permanganate, and when you do stoichiometric analysis, you can essentially determine moles of iron +2 +3 converted is equal to 5 times the moles of MnO4 minus, like that. So when using the stoichiometry, you can relate it to the equation via this relationship. It's a 5-to-1 reaction ratio. So if you can determine what permanganate ion concentration is after the titration, then you can determine the iron concentration by multiplying by 5. Iron will be 5 times more than whatever the permanganate ion concentration would be to reach the equivalence point. And we'll talk about the solution. I can put it in now. Each of these, if you know the concentration and the volume of one or the other, you can find molarity, M, times volume, V, is equal to, and express that in liters, is the moles of reagent. So you can take molarity times volume of the iron equals 5 times molarity times volume of the permanganate. Excuse me. Actually, you can leave it in milliliters if you want, because both sides of this equation will be in, will have same terms. Molarity of iron times the volume of iron solution is equal to the molarity of MnO4 minus solution times the volume of the MnO4 minus used in the titration. So in this expression you can calculate the molarity of the MnO4 used, and this should be multiplied by 5. Okay, we'll get to some more of that later on. Then you can determine the molarity of, from this, your unknown would be, of course, excuse me, over here, the molarity of the iron converted is equal to the amount of iron 3 that is formed. Okay, now let's develop the stoichiometry of the titration analysis a little more logically. To begin with, what we want to understand is mixing of solution phase reagents in, say, a water solvent can be related to the reaction equation that you're using to study the relationship of. This essentially refers to relating the titration process variables, we'll get to that, to the balanced chemical equation representing the reaction of interest. Now, what are titration variables? Include volume of your titrant, molarity, of the titrant, volume V of the solution of interest, that is your unknown concentration, and the solution volume of the solution of interest having an unknown concentration, and the molarity M of solution with unknown concentration. Now, as we mentioned a moment ago, if you want to relate these variables to a chemical equation, you must take this information that you derive from the titration and convert it to moles. And then you can apply it to the chemical equation, since of course the chemical equation is based on mole quantities. From the definition of molarity, we can derive the relationship between moles and titration variables. That is, molarity M is equal to moles solute over volume solution expressed in liters. And if we solve this expression for moles of solute, this would give us molarity of the solute times the volume of solute solution. And of course, that's expressed in liters. So you can convert this data to mole values, which you then apply to the chemical equation to determine stoichiometric amounts needed, added, or what's in excess, what's not in excess, and so forth. A simple example, let's say we have, say you're given a reaction where A plus B goes to AB. Simple enough. Well, if the reaction is balanced, moles of A equal moles of AB produced, moles of B equal moles of AB produced, and A and B are both equivalent in mole amounts. So we have 1 mole A and 1 mole of B. Easy enough. But when we do titrations, the quantity of A or the quantity of B being titrated will be given in terms of a molarity of A, say, and a volume of A. And the moles of B will be given as molarity of B times the volume of B. And since they're equal, we can set these two equal. Now, since both sides have the same term, units, you do not, in this case, have to convert to liters. However, if you don't have one side or the other, if it just says molarity volume equal moles, you have to deal with it in terms of liters. From a practical standpoint, if in a titration either solution concentration is known, then the concentration of the other reagent and reaction can be determined using this relationship. So if we don't know what the molarity of, say, B is, but the volume of B is specified, and the molarity of A is, say, known, because you prepared, say, a solution of A, and the volume of A used right there to get to the appropriate equivalence point. Then you can calculate the unknown. It'll be an equation in one unknown. Okay, now what we want to look at is a simplified titration process graphic to get a practical or real perceptive concept of what's happening in the titration process. And in this, it is a titration burette in which we will put the titrant solution having the known concentration, and in the Erlenmeyer flask here, or beaker, whatever you want to use, appropriate, be sure it's clean and neutralized, a volume of solution of the titrant, of the solution of interest. Now the issue is, what is the concentration of the solution in the Erlenmeyer? Now you could put the unknown in the burette and the knowns down here in the flask, whatever your personal preferences are. I like personally to put the concentration of the known in the burette and titrate it into the unknown. Let's say hypothetically we are titrating sodium hydroxide into a quantity of hydrochloric acid, and that will produce a solution of sodium chloride ions and of course water, like that. Now what I'm going to do is put some acid in here in the form of red dots, and my base down here in the form of blue dots. Okay, now as the reaction proceeds, well, I'm going backwards, sorry. Let me fix that. Now, sorry about that. Anyway, as the reactions proceed, when a blue dot comes in contact with a red dot, we produce some salt. And let's use, say, a purple color for our salt. As the simplified version goes. So now, as we open the stopcock of the burette, we will be allowing some of the acid into the Erlenmeyer flask, and it will start neutralizing the base, the blue dots. As it does, it will start out with an original volume right here, and will move to some point down here, which will represent the volume that you will use. So what we're going to do when I open the stopcock, of course the one down here is going to go in, but it's going to drop in volume by the loss of the amount that you put in, and the solution now has a salt in it. Now, the HCl is the limiting reagent because we have a small amount of that going into the solution, and there's such a large excess of base. Any acid that's added in at this point will be completely consumed 100%, and we'll have some base left over. Well, we're going to add another quantity of acid, and so we neutralize some more of the base. We'll add some more base, and we've neutralized this much, and we'll put one more just for interest's sake. Okay, we're halfway to the equivalence point now. Equivalence point, you recall, is when all of the reagent has been converted into salt and you have no acid and base remaining. Okay, there will be only salt at the equivalence point, and of course new water if you want to think about that. So we add a little bit more acid and we continue, and a little more acid, and then we add a little more, and at one point in the titration we will have reached the equivalence point. So what you need here is the volume final at equivalence point right here. All right, and then if you started here at say 0 milliliters, your volume used is of course the volume used now is whatever you read off the burette at that point. Now you have a known concentration of acid and you have a known volume of acid used. Now at this particular point you have a volume of the base volume, and so the issue is, well, what is the molarity of the solution or base that you've neutralized? Well, for every 1 sodium hydroxide we'll neutralize 1 of the acids and convert it into salt. So the moles of, in this case, moles of acid added equals moles neutralized. Now, using the relationship that I showed you a moment ago, that moles is equal to molarity times volume, we have the molarity in this case of HCl times the volume of HCl added is equal to the molarity of the sodium hydroxide times the specified volume of the sodium hydroxide solution. So in this particular case, this is your only unknown now. So you can solve this expression. You take the data, like the volume here that is used right here, the molarity, because you prepared the solution, and the volume known right here, and solve for the molarity. And it's an equation and one unknown. And so that you can determine the concentration of the unknown. There's one other little element that I want to share with you here on this. If we continued to put additional acid in from this point on, after that point, there would be nothing for the acid to react with. it's not going to react with the salt. So we would have just some excess acids in the system as we put extra acid in the salt. Now, if a pH electrode is inserted into the base solution, then you can measure the change in pH as the acid is added. That is, you can measure the change in alkalinity of the solution you're titrating as a function of the amount of acid added. That is, the alkalinity changes in terms of pH, and the acid addition is volume of acid added. Now, since we're starting with a base solution, you'll find it would be up around between 13 and 14. Let's just say 13 right there for this pH range runs from up to 14. Okay, anyway, if you recall, as we added the acid in, some of the base is neutralized. So if we added a small quantity of acid onto the sodium hydroxide, we'd find or could start adding HCl in small quantities, we'd find the trend would start moving toward the acidic end, start getting more acidic, which is down in here. So I'm going to say pH of 1 if you want to. At some point in here, which is very, very close to the equivalence point, say in a very small volume region, you'll find when you start getting close to the equivalence point, start neutralizing these last few sodium hydroxides or bases, the pH will change very, very rapidly with small additions of acid until you get beyond, say, that small window, and it will begin to level out in the acidic range. The point in the middle of this inflection which changes from a slope, negative slope, to a vertical, then back to a positive slope maybe, or just what you're looking for is a vertical slope where it is, the second derivative is 0. We could simply say it's, and I'm eyeballing this, say right there. Okay, some issues that you need to learn about relative to what's going on at the equivalence point, that is, once we have reached complete neutralization. So some people call this the neutralization point of an acid-base, strong acid, strong base reaction. Now, this is one issue that's very important that you understand. Only sodium chloride, well, new water if you want to throw that in, but for practical consideration, only the sodium chloride remains in the beaker or the flask, whatever you're using when you titrate. All of the acid and base, whatever was in that, added into that flask, has been converted to salt. That is, you have 0 acid and 0 base at the equivalent point, the original acid and base. Now, if we were working with weak acids or weak bases, then you would move after that to consider things like hydrolysis effects of the salt. But that's not what we're dealing with here. I just want to get the basic strong titration concept across right now. If this is a true strong acid, strong base titration, I can draw draw a line from the equivalence point to the pH axis and a line from the equivalence point to the volume axis, we'll find that the pH at the equivalence point for a strong acid, strong base titration will be 7. And this volume right here is the equivalence point volume. It's very important that you understand there is absolutely no acid or original acid and base in the system. This is an important implication as you move forward and talking about determining reactive ionization constants of weak acids or weak bases. You can determine those using the titration curve if you understand the idea of how the concentrations change as it proceeds through this titration curve. Now, just to summarize the data that you are deriving from this graphic or titration curve, you have the molarity of the acid, and that is a known, known concentration. Volume of the acid is measured as you approach the equivalence point, so you're trying to find out where the equivalence point is. Molarity, I'll put it over here. I'll try to get it in here. Molarity of the base is the objective, is the unknown, and the volume of the base is, you choose that, it's a specified at start of titration. So you want those 4 variables and understand where you get them. You made the acid solution to add into the base solution, so you should know what that is. You measure the volume of acid that you add during, you recall, that would be adding the acid into the solution until you reach the equivalence point right here, so you know the acid concentration and the volume used. Now you can calculate the moles of acid, and you specified what amount of volume, that is, of base you put into the receptacle beaker receiver. And so all you have to do is calculate the unknown. In this relationship, it's a 1-to-1 relationship. So we can say moles of acid used neutralizes moles, a certain number of moles of base in the beaker or flask. Moles is molarity times volume of the acid, and that's equal to molarity times volume of the base, and this is the only unknown now. So we can set up a simple equation: molarity of the acid times the volume of the acid, so equals the molarity of the base times the volume of the base. And if we solve this for the unknown here, we have the molarity of the base to equal molarity of the acid, known, volume of the acid that you measured to reach the equivalence point, and the volume of the base you specified at the beginning of the titration. And so substituting your known values for the acid and the volume used of acid and the volume of base specified, you can determine the unknown molarity of the base from the titration data. There's volumes of information that you can still derive out of a titration curve and use for discovery, and those will be covered in due time. But right now, I want to work through an example of a titration and show numerically how it is used to determine an unknown base. Okay, as an example, we want to look at the titration of an acid solution, and I didn't write it in, but an acid solution into a base solution. Here's an example that's rather standard in these types of situations. Let's say if 25 milliliters of 0.30 molar hydrochloric acid that you made is sufficient to neutralize or achieve the pH of 7 if you're monitoring, neutralize the base solution, 30 milliliters of a sodium hydroxide solution. What's the concentration of the sodium hydroxide solution as based on this titration data? Well, HCl and NaOH, the first thing you need to do in problems involving titrations is write down the appropriate equation so you can see what the mole ratios are in the equation. If you're using sulfuric acid, it's going to be an H2SO4 trying to neutralize the base. In that case, you're not going to have a 1-to-1. You're going to have a 2-to-1 reaction ratio. We'll get to that in the future. But right now, for 1-to-1 reactions, sodium chloride and sodium hydroxide react 1-to-1 to produce sodium chloride plus water, as shown here. Now, a simple data sheet would suffice. Why don't we start out with the molarity of HCl? Well, the problem says it's 0.3 molar, 0.30 molar. And it says you only use 30 mils of the, 25 mils, I'm sorry, volume of HCl used is equal to 25 milliliters. Now, for the base, the molarity of the sodium hydroxide is the object of the question, the problem, and it's certainly unknown. You prepare a solution of your sodium hydroxide and you measure out, and I just chose 30 mils for the sodium hydroxide solution, milliliters. Now, since the moles of HCl equal the moles of sodium hydroxide, then we can use the molarity times volume to calculate the moles over here, and molarity times volume to calculate moles of sodium hydroxide and set them equal. So we have molarity of the HCl times the volume used, HCl used, is equal to molarity of the sodium hydroxide, which we're trying to find, times the volume of sodium hydroxide specified at the beginning of the procedure. Okay, now solving for the molarity of the sodium hydroxide, we have the expression molarity of the hydrochloric acid times the volume of hydrochloric acid used and divided by the volume of sodium hydroxide specified. Now, since the equation has same units on both sides, we can leave this in milliliters. Okay, this is an exception. But if you're only determining moles and you don't have another side to an equation, if you want to know the exact moles of HCl that applies to this data, you have to convert this to liters. Okay? So I'm going to leave it in milliliters just for this occasion. Molarity is 0.30 molar. Volume of HCl used is 25 milliliters divided by the specified 30 milliliters of base. Milliliters will cancel out. Whether you convert it to liters or milliliters or leave it in milliliters, it's still going to cancel out and give you the same number in the ratio. 0.025 divided by 0.030 still gives you the same number. And the outcome of this is 0.25 molar sodium hydroxide solution. Of course, that's aqueous right there. And so that is the, quote, answer to the titration problem. Now, one other type of problem that arises on many of the exams and studies that you'll do is questions like, what's the final molarity of a solution after you mix a specified acid solution with a specified base solution, such as, let me see. Okay. The issue is determining excess acid or base upon mixing specified volumes of acid and base solutions, both having known concentrations. And here's an example that we want to work through. After mixing 45 milliliters of a 0.15 molar HCl with 38 milliliters of a 0.22 molar sodium hydroxide solution, which reagent will remain in excess, and what is the molar concentration of the reagent in excess? I'm going to move this up. It gives me a little more room here. When approaching a mixing problem like this, what I find useful is to first work relative to the equation of the reaction, like this: HCl, aqueous, and space a little bit more normally, NaOH, aqueous, will produce the sodium chloride, aqueous, plus H2O as your weak electrolyte. First, let's mark down the acid solution. I do it like this: 45 milliliters of 0.15 molar HCl, okay, plus I've got 38 milliliters of 0.22 molar sodium hydroxide. Now, with this, I want to convert this to moles and sodium hydroxide to moles. Compare to the NaOH mole, compared to the reaction, which is a 1-to-1 reaction. The component of the two, which is larger number, is the one that will remain in excess, because the one is larger in moles. You're only going to use a fraction of the total amount there. Now, again, in this case, to get moles, you don't leave it in milliliters. You have to convert it, this kind of problem, to liters. So in this case, 45 milliliters would then become 0.045 liters times 0.15 molar HCl. So that times that will give you moles of HCl, which we'll write down here. And you're reacting that with 0.038 liters of 0.22 molar of the sodium hydroxide. Now in this case, 0.045 times 0.15 will lead me to a 0.00675 mole of HCl added to this solution, which is 0.0836 mole of sodium hydroxide. Right there. So if equal amounts have to react, because that's what the equation says, 1 mole of this, 1 mole of that, 2 moles of that requires 2 moles of that, 0.00675 will use only 0.00675 mole of sodium hydroxide. So to find out what is left over quantitatively, I need to subtract 0.00675 from 0.0836. So I'm going to come down here and minus 0.00675 mole, and then out here I'm going to specify NaOH neutralized. Okay. Won't ruin my thought. Anyway, when this is subtracted, we have 0.00161 mole of NaOH remaining. In excess. Okay, that's moles. It is not molarity. It is not the concentration. What is the molar concentration? This ain't it. But it is the one in excess. To get molarity, or convert this to molarity, you apply the definition of molarity. And so molarity of the NaOH solution now is defined as moles of solute divided by volume of solution expressed in liters. Okay, I may have to lose some of the problem, but your moles of solute, which is your excess sodium hydroxide, is equal to 0.00161 mole in NaOH, and that's the solute that remains in the solution. It's got sodium chloride in there, but this is in addition. Okay, the volume of solution is the volume of the acid plus the volume of the base. That's you poured one on top of the other. In milliliters, you added 45 milliliters of the acid plus 38 milliliters of the base. So that gives us a total of 83 milliliters final solution. Now, of course, that has to be expressed in liters, so that'd be 0.083 liters for the final solution. So we want to apply 0.00161 and 0.083 to this expression right here. Well, I guess I can move it up here. Let's see what we can get here. 0.00161 mole sodium hydroxide excess divided by 0.083 liters solution, which leaves 0.01949. molar in sodium hydroxide, which you could round off right here to 0. Sorry, look at a mess. Okay, cleaning up my mess. So anyway, molarity is moles over volume in liters, 0.00161 mole of sodium hydroxide in excess divided by the total volume of the solution. We get 0.019 molar, which could be rounded to 0.020 if you wanted to carry it 2 sig figs. If you wish to carry just 1, that's fine. But you have the excess and the concentration of that excess in final solution right there. Now there's some other kinds of conclusions you can draw from titration analysis also, and I'm just going to put those down even though we haven't gotten to it formally in the lectures. You would have something like what is final pH, or something like how much acid or base, whatever the case may be, would be needed to neutralize specified solution. Something of that nature. Or if you were working with a salt-salt precipitation reaction, what volume of specified salt would one need to start precipitation of product salt. From given salt solution data. And we'll talk about that when we get over into solubility product equilibria. Of course, don't forget calculate molarity at equivalence point, and the titration curve may show up as an base into an acid. If it's a base into an acid, your titration curve would follow this trend. And if it's a strong titration, of course your equivalence point pH would still be at this position right there. And as we've shown in the example we used, if we have acid into base, we would probably be monitoring what's in the beaker, and it would follow that trend. Now if there's strong acid, strong base titrations, right here, pH for either one of them, whether you're going acid into base or base into acid, is going to be 7. if you prepared your solutions correctly and you have absolute perfect neutralization. Well, that's about the size of some of the titration problems and titration issues that you will be responsible for over the near future. So please invest as you need.